So now we're going to switch to a new topic for interrupts. So interrupts in a computer are requests. So it's like raising your hand in class. There's one teacher. She can't handle everyone talking to her at the same time. So we raise our hand in polite, well, we used to, in my day, we'd raise our hand and say, I would like to say something. So she would call on you and say, yes, can I help you? So nowadays, you might just bark it out at them, but back in the day, we used to raise our hands. So this is the same analogy here. So interrupts, say you have, I'll give you a not so real example and then a real example. So say you have the teacher talking to someone about answering a question. And then all of a sudden you think of another question, so you raise your hand and the teacher would say, yes, sir, can I help you? So then you tell her your question. So you're talking, you've interrupted the other one. So that's where the interrupt comes from. So in digital signaling in computers, the same thing happens, but the CPU only has so many interrupt requests. So because everything's electrically connected and you can't have infinite connections. There's only so much limited stuff. There's only so much memory. So the way it's set up is depends on the computer, it depends on the CPU. Again, this is an evolution. Everything gets bigger and bigger and bigger as things go along. So the earlier you understand this stuff, the easier it is to learn it as you go on because you're just kind of tacking on to what you already know. So system interrupts are access requests for processor time. So what happens is the electrical connection says, so like one way you can generate an interrupt is when you're blocking on a TCP port. So say you have a communication session going. Say we're in an industrial control environment, and you have a process that's mixing paint, and the paint mixer says, "Okay, I'm ready to start mixing paint." So it's not mixing paint yet, but it's ready to start mixing paint. So everything says, okay, the paint's been poured into the bucket. We've put this other color in there. Now it's time to mix the paint. So it would send a signal over to the computer, and the computer might receive that over a message. It might receive it over a wire that gets translated into message. But anyway, it's going to get bubbled up into the CPU at some point via a wire. So realistically, what will happen is it'll come over TCP, over the wire. And the computer is waiting for messages to come from the paint mixer because it already told it, hey, go put the color in the bucket. Then it comes back and says, hey, I put the color in the bucket. Then there's an interrupt to the computer and it says, hey, we already filled the paint bucket. And the computer goes, oh, okay, I'll go ahead and start the color now. Or you put the paint color in there. So let's say we put a thinner. So we need to add some thinner. So the computer says, oh, okay, I'll add the thinner now. So then it sends a signal out to this machine listening and says, oh, you ready to add the thinner? Okay, here we go. And then it sends a message back to the computer, which is just waiting. The computer is what's called blocking mode. So that little port way down in the weeds somewhere is blocking. It's waiting for that message. There's a little process running that's waiting for that message. So the message arrives on the port. It bubbles it up to the process. The process says, oh, okay, we got the thinner is already added. So now we need to start mixing. So it sends an interrupt request to the processor. Hey, kick on the motor for the mixer because we've got the color and the thinner. So the computer says, okay, and it sends out the message down to the paint machine and says, okay, start spinning, start mixing. So it starts mixing. So then when it's done mixing, it'll send another request back over to the computer. So that's how things work in the computer. So there's two types of things. There's polling and there's interrupts. So two types of drivers, right? So they're interrupt driven. Processes are either interrupt driven or they're polling. So like a keyboard can be interrupt driven or it can be polled. So in the case of a keyboard, a human can only type so fast. And the way these work, the way the keyboards are designed, they have a little chip in them. And when you type and you press a key, you touch the key for just a fraction of a second. I don't care how fast you try to get your finger off of the key. The computer's polling so fast, it's going, did you press, 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 through every single key on the keyboard. Did you press, did you press, did you press, did you press? And if you pressed it, it's doing it so fast that it's going to look at it while you're touching it. That's how fast it's happening. So you'll never miss it. So unless there's something wrong in there, like that's tying up the processor, as you press, it may miss the request. But eventually, while you have the key down, the processor will poll the buttons and see if they're being pressed. So you can't let it go fast enough that the processor won't miss it. Hopefully that makes sense. So that's called polling. So in other words, back to the teacher analogy, just to hammer this home, you might say, did you ask a question? Did you ask a question? Did you ask a question? Which is very annoying, and it's a lot of work for the teacher, and she can't do anything else. So that's literally why interrupt-driven requests were made, and we abbreviate them with IRQs. So let's run through the bullets here. System interrupts are access requests for processor time, or to notify the processor of something. The processor will respond to IRQs, interrupt requests, before processing anything else. The second an interrupt happens, the computer gives it a very quick time slice to go and handle the interrupt. Now, I guess I should caveat this a little bit deeper. So when something is blocking, it will wait forever for that message to come in. And the only way it's going to get there is through an IRQ, an interrupt request. So they will wait forever. They're just sitting there. So the way a computer works, they do multitasking. They do not do everything at once. The computer does one thing at a time. So we talked about switches earlier, and that it electrically connects where the message needs to go. So the processor does one thing at a time. A switch makes one connection at a time. But how does it get the messages? Do the messages just wait in the switch before it goes up here if this one's talking? No. It just lets a little bit go here, a little bit go here, a little bit go here, and a little bit go here. So to you, this happens so fast. So to the human, you think it's all happening at once. Just like when you're watching a movie, the frames go by so fast that your eyes can't detect that things are changing. So it's the same way. It just happens so fast, it seems like it's all happening at the same time, which is where real-time programming comes in. It's just fast enough to get things done where you don't perceive it that it's not happening. So with interrupt request, things that are blocking will block forever. They will eat up RAM, CPU, and everything. But what happens is when a program is blocking, it still gets processor time. The processor goes to each process in memory, and says, do you need anything? Do you need anything? Do you need anything? It'll let the program execute for a fraction of a second, let this program execute for a fraction of a second, and execute this program for a fraction of a second. So this one does a little bit, gets paused. This one does a little bit, gets paused. This one does a little bit and gets paused. So those are called, when it switches from one process to another, those are called context switches. So it's switching between each application. And a lot of overhead goes into that switch. So you don't want to do them too fast because nothing gets done. So if you have too many processes running, each one gets tighter and tighter as far as cycles go. So what happens is you drive it into something called thrashing. And what thrashing is each program, the computer has so many processes and the time cycles are divided up so far that there's no time left for the application to run. The computer can only load this thing into memory, let it run for maybe one cycle, and then it switches it out, or it may load for no cycles. It just swaps it in and swaps it out. It never gives it enough time to run. So it swaps it in and swaps it out. It's performing context switch, context switch, context switch, and no processing. So what happens is basically it's in thrashing, and it'll never get anything done, and eventually it will crash. So that's what's referred to as thrashing. Not a text question, but just to kind of hammer home the difference between polling and interrupt-driven so you understand what's happening there. So interrupt-driven is a lot better, it's a lot faster, it's a lot more efficient, but for some things, polling works. But you don't want to poll with the CPU, you want to poll with other little specialized systems out there. Polling rates, if they need to be really high, that's costly and expensive. So something that needs to be polled very often might be better off in an interrupt-driven environment. So let's see, I was going to tell you about that. These are utilized through rogue code and things like keyloggers to perform their work. Yeah, so like Zeus, for example, is a interrupt-driven malware, so it uses interrupts. And then, so a blocking program will sit forever and blocking until an interrupt fires off. So if you never get the interrupt, nothing will ever happen with the blocking program. So you can consume resources if you can keep something blocked forever, and nothing will ever happen inside the application. DHCP, Dynamic Host Control Protocol. So this is a protocol, and this is how When you plug a computer into the wall and it pulls an IP address, it does it through DHCP. DHCP is a server that you configure, and it can be programmed to give the same MAC, the same IP address every single time, or it can just randomly rotate them with an expiration date. So it might be good for 1 week, it might be good for 1 day, it might be good forever. So DHCP answers requests for devices requesting an IP address on the LAN. They're configured to use specific address ranges and can be configured to give the same MAC address, the same IP every time. We talked about that. Can be configured to rotate the IP addresses at specific rates, roll the IPs every hour, every day, every week, etc. There's some people out there that are trying to roll the MACs with strategy at random times so that malware gets all messed up when they're trying to report back and things like that. Kind of crazy stuff. Some tactics that they're trying.